Swayam Prabha. Digital India. Educated India.
Hello everyone. In today's class, we will develop the code for solving nonlinear convection problem as well as the shock tube problem. Okay. So, we have looked at many schemes. Let us see how they behave when the problem is nonlinear, and finally solve a proper fluid dynamics problem, that is the shock tube problem. Okay. We will use the Schwartz condition, give the pressure jump and the density jump, and see how basically are you able to capture the shock traveling on the right hand side, basically the pressure jump, density jump, velocity jump, and so on and so forth. Okay. So, let us start with a nonlinear convection problem first. Okay. So, here you can see that instead of c du by dx, we have this del by del t plus u del by del x. Okay. And if you want to solve it, okay, so the better way to basically do it is basically change it to del u by del t plus del f by del x. Okay. So, let me just do that. Okay. And then you can, what you can do, you can add f is equal to u square by 2, right. So, that will be u square by 2. So, this is the way you can solve it. Okay. Okay. So, this is my function. Okay. Let me make it big little bit. Okay. And we had seen the behavior in many different cases. So, in exponential function, sine function and Heaviside function. So, we already saw how they behave for the linear problem. Now, we want to solve the nonlinear problem and see how they behave. Okay. So, the code remains the same. The only change that I have made, that I have introduced this function called fun, okay, that depends on x, and if it is a linear problem, for example, this is just x, okay, that means your convection speed is 1, and the problem that is solving is del u by del t plus del u by del x equal to 0. Okay. And if you are solving a nonlinear problem, which is the nonlinear convection, so this become 0.5 x square, that is basically if x is equal to u, that is half u square. So, basically this problem. Okay. So, let us start one by one. So, we will start with the Heaviside function, okay, or the step function, and let us see how they behave. So, we already know the initial condition, and so what I will do, I will start with the upwind scheme. Okay. So, let me start with the upwind scheme. Before that, I want to show you the code. Okay. So, now I have basically changed it. So, earlier I was calculating lambda equal to c dt by dx, and I was doing this lambda into ui minus 1. Okay. So, that was my earlier code. I can probably show it to you here. Okay. Yeah. Here this was the code earlier. So, lambda equal to c dt by dx, and here this is the very important term, you multiply lambda into ui minus 1. Okay. So, I am using the same name lambda, but this is nothing but dt by dx. Okay. And I just change ui to fi. Okay. And what I will do, I will just first use the function which is a linear function. So, function is just at the rate of x. So, f is equal to u. Okay. So, solving del u by del t plus del u by del x equal to 0, and look at different schemes. Okay. Start with the upwind scheme. Okay. Let me run it. Okay. So, as expected, this is not McCormack. Okay. Just let me change the legend here. Okay. This is an upwind scheme, and behavior is same as the linear convection equation that we saw earlier. Okay. You can use, I mean, many different schemes, and they will all probably give you the same solution. Okay. Similar solution. Okay. Just let me uncomment this. Okay, so I have upwind scheme, lax wind up scheme, sorry, lax fatigue scheme, lax wind up scheme, beam warming, McCormack and Richtmeier. Okay, uh, but I have think I have not coded for all of them. So let me just do this. Okay. Okay, so I think the grid is very coarse. Okay, so I have used only 51 points I behave. This NX is just 51 points, but this is how the different codes behave. Okay, if I can write it here, so this is analytical, this is initial rather. Okay, then upwind, then Lex Frederick, then beam warming. Okay, and then you have McCormack and Richtmeier. Okay, all these schemes I have implemented. We already saw the implementation yesterday. Okay, so let's do run section. Okay, you can see that for example, schemes like upwind, okay, there is a lot of dissipation, but it gives you decent result. Then we have this beam warming, this is upwind biased scheme, and then in the case of McCormack and Richtmeier, basically these both are two-step schemes. Okay, so they show a lot of wiggles, and Lex Frederick also has this behavior. You can probably try increasing the grid size. Okay, so let me just increase the grid size to a very high value. Okay, let's make it 1001. Okay, and then just run. Okay, it blew up. Okay, maybe I can just change it to 501 and let me just see what is the lambda. Okay, so lambda was very high. When I decrease the grid size a lot, the delta x become very small, and lambda was 1.667 that you can see. That is why the schemes blew up. Okay, so to be very careful what value we are using. Okay, and if you now I am using a value which is 500. Let us see what is the lambda value here. Okay, lambda is 0.833. Okay, and you can see in this case, okay, they all basically try to predict it pretty good. Of course, in the Richtmeier scheme and the Lex Frederick scheme, you have lot of oscillations. Okay, this would be the analytical solution. Okay, for the linear case. Okay, where it is moved on the right hand side. The upwind has got some dissipation. Maybe I can basically make it slightly bigger. Okay, so upwind has got dissipation. Beam warming is lesser dissipation than that. Lex Frederick has got even more dissipation. Okay, the yellow line that you can see here. Okay, the others are predicting better, but they have got oscillations. So, they have got dispersion error. Okay, now let us try making it nonlinear. Okay, so I will be commenting this function and I will use the nonlinear one, and I will decrease the grid size to the old one because I know that schemes will behave very poorly. Okay, when the CFL number is high. So, remember this is now a nonlinear problem. So, the CFL is for a given CFL your delta T is not constant, it is changing, right. So, if you use the same delta T as you calculated earlier and try to simulate it, it might blow up also because of the U plus C may become very high. Okay, and so just run it. Okay, so here you can see one interesting behavior that we have discussed earlier also is now it is basically tilting towards right. Okay, the right side is basically it's more vertical than the left one. That means it is going towards developing a shock. Okay, and once again the upwind or upwind biased schemes like beam warming, they are doing better than or other schemes. Okay, for the nonlinear problem. Okay. let us say if you want to change it to exponential function. Okay, I will change my input function to an exponential function and run it again. Okay, see how the behavior is. Okay, so this is now an exponential function. Okay, it is a much smoother function. So your Lax Frederick behavior is much better. Okay, but although there is a lot of dissipation here. Okay, Richtmeier is showing you some kind of dispersion here. Okay, McCormick also is dispersion. Remember, for the linear problem, both Richtmeier and McCormick are like Lax-Pandorf. Okay, so they will have dispersion, and the beam warming is showing very little dispersion here, but it has got the lagging phase error. So that is why you have this dispersion that is coming here. Okay, so let me just switch off those beam warming part, all those things. Okay, yeah, just to see a cleaner diagram. Okay, so Lax Frederick has got higher dissipation. Okay, so that is why it behaves like this. The upwind is better than the Lax Frederick here. Okay, but you can see that instead of maintaining a symmetry here, now it is tilted towards right. Okay, so that is due to the non-linearity. Okay, now let us with this understanding that we can change, you can use a function instead of the speed of sound or the c, the convection speed. Now let us try to solve the shock tube problem. Okay, so this is our shock tube problem, high pressure and low pressure, and this is the initial condition. So left hand side will do rho L, PL and UL, and right hand side will put rho R, PR and UR. Okay, and we are solving these Euler equations that we have discussed earlier. These are the formula for primitive to conserved, conserved to primitive, and similarly you can have the formula for calculating flux. Okay, this is the line for calculating it using analytical approach. You can get it from anywhere, that is not very difficult. You have to calculate the shock speed and find out the position of the shock. Okay, and these are the functions that I have written. So I have used a function called deal in MATLAB. So what it does is that it can give you multiple output in this anonymous function definition. So when you write fun equal to at the rate of, let us say if I am writing fun is equal to at the rate of x. Okay, and then x is y. Okay, okay, let us say this is your function. Okay, so this is called anonymous function. Okay, so it takes the input x and gives you back x square, right. So if you let me just define it here. Okay, I have defined that, and now if I do just fun 2, okay, so that will give me the value of 4. Okay, if I use fun 3, okay, that will give me the value of 9, right. So this is giving me x square, right. So similarly, so here there is one input and one output. You can have multiple input and it will typically give you the one output, but if you want to use anonymous function with multiple output, because I have 3 vectors q1, q2, q3, f1, f2, f3, u1, u2, u3. So I use this function called deal. So this can basically give me 3 output, right. So for example, this is p to c, primitive to conserved. So I am giving rho u and p, and I am getting rho u, rho u and rho u square plus p, right, p by gamma minus 1, right. So this is what is doing here, rho u and rho u square plus half rho u square plus p by gamma minus 1, right. So this is my primitive to conserved. Okay. Similarly, you can do the conserved to primitive, where we am giving this q1, q2, q3, and I am getting the primitive value, which is my rho u and p. Okay, this is what q1 and q2 by q1, which is basically rho u by rho, that is u, and this from the energy we are getting the primitive variable, which is p. And similarly, you can calculate the flux from q1, q2 and q3, as we discussed in the last class. Okay, so these fluxes are basically rho u square plus p and rho e plus p u. Okay, this is now I am using directly the conserved variable to calculate the flux. Okay. So, I hope you understand how this what these functions do. They take these as input and gives you the output, which are the 3 outputs for each case. Okay, I am taking length is equal to 1. So, basically I am taking from minus 5.5 to plus 0.5 is minus L by 2 to plus L by 2, taking n is equal to 501. So, this is 500 grid points, and these are just some allocations. Okay. So, I am allocating. So, I have defined this as primitive variable u, p and rho. R is my density and a is basically my speed of sound. Okay. And q1 f, as I was telling you, it is a vector, and all 3 will be updated at the same time. So, its array size is 3 cross n, where n is the number of grid points. Okay. Similarly, flux is array 3 cross n. Okay. Now, you can give the initial condition. So, this is uh, the value that we have, okay, for p infinity, row left and row right, and so on and so forth. You can see the p1, which is the p left, is p infinity, and p2 is 1/10 of the p infinity. Okay. And then you can assign it on the left hand side 1 to n by 2 and then n by 2 to n, row 1 and row 2, and u is 0 anyways in the initial condition. I am using a CFL of 0.5, and I am calculated the speed of sound gamma p by rho, and then I have basically you can see it better probably. Okay. And dt is calculated CFL into dx divided by maximum of absolute u plus c. Okay. And I calculate the number of time steps. Okay. How many time steps I need if I have this t end, which is basically 0.1 second. I want to get it at 0.2 second. Okay. So, how many number of time steps I need. Okay. So, after this we can start solving. Okay. And from this row u and p, you can calculate the variable q1, q2, q3. Okay. This is what it does, p to c. Okay. And I will show you the schemes here also. Okay. So, the McCormack scheme. Okay. Instead of now you have f here on the right hand side. So, this is a predictor step. Okay. Calculate the value of u star. From the u star, I calculate the f star, use the value of f star here. Okay. This is a predictor character. This is what I am doing here. Okay. So, just so. Okay. Yeah. So, this is my this is McCormack. So, this is the predictor step. Okay. Sorry, this is how I calculate the flux for the given q. Okay. Calculate qp, which is my predicted q. Then from this qp, calculate the flux again. Okay. And then that is fp, and then use that fp here. Okay. To save memory, I have used the fp and both the variable before the prediction and after the prediction, but you can use f instead of fp, you can use f here. Okay. So, this is the predictor step. Okay. This is 129, and this is my corrector step. Okay. Which is half of the basically summation of q1 qpi, and then lambda into fpi and fpi minus 1. Okay. This is the McCormack scheme. Similarly, you can have the Richtmyer scheme, where you have Lex Frederick at n plus half. Okay. So, I am not doing the 2-step Lex Frederick, but I am doing the Richtmyer, which is basically we do not have to do this I plus half and I minus half business. Okay. So, just calculate the predictor, which is ui n plus half, okay, using Lex Frederick, and the second step is do leapfrogging. Okay. That is what I am doing here. This is my Lex Frederick. Okay. You can see that I am taking average of I plus 1 and I minus 1, and then I use this leapfrogging the next step. In between, I have to calculate the flux. Okay. I am also using the Lex Frederick scheme. Okay. And as we know, there is a lot of dissipation in this, but it gives you some result. So, initially, in fact, if you are trying out CFD, try out a scheme which is dissipative, so that you do not have to basically worry about a scheme blowing up, okay, solution blowing up. But after you become comfortable with these schemes, try to use a scheme which has got just right amount of dissipation, so that you do not get lot of dissipative error. Okay. So, this is the Lex Frederick scheme. Again, there is a flux here. I have to calculate flux only one time, this single step scheme, and this is how I am calculating this QC, which is the variable that I want. This is what gets returned. Okay. Now, let us plot it. Okay. Use maybe one scheme at a time. Okay, so I will calculate this using Lax-Frederick. Okay, so this is the Lax-Frederick function I am calling at for the nth time step. Okay, doing it will give me the conjugate variable q. Then I basically use those conjugate variables to calculate my rho, u, and p. Okay, and then I am plotting this rho and x. Okay, so let us do that. Okay, I will run this. Okay, so you can probably see it here. Yeah, not sure if you can see it or not. Okay, this is a movie. So, you can see that now it is dissipated, but you have this expansion region, expansion fan, there is a shock here, and in between you have this discontinuity. Okay, let me play this again, how this flow gets developed. Okay, run section if I do. Okay, so you can see that let me just do it, do not limit the. Okay. Okay, I have not limit the limit rate. Okay, and let us see this. Okay, run section. Okay, you can see that how this is the flow is developing. Okay, so you can keep watching here. So this is moving, and a shock will develop. Okay, a shock is already developed. Okay, but I am waiting till it goes t equal to 0.2 second, and ultimately when it goes to the 0.2 second, you will have a shock at that position. Okay, so slowly you can see that structure getting developed here. Okay, yeah, you can also see that now that the contact surface also got developed. Okay, because the density contour. So, you can see that contact surface also, and this is uh, the expansion region. Okay, let's stop it here. Okay, you can probably see your pressure also. Okay, so instead of density, let me plot pressure. Okay, and run section. Okay, so you can see this is the final pressure here. Okay, at around 0.2, and this is shock and the expansion fan. There is no discontinuity in this. You can also plot maybe the velocity. Okay. Okay. So, this is the velocity that you see here. Okay. You can change the scheme. So, if I just change the scheme from Lex-Frederick to, let us say, do Richtmeier. Okay. Do run section again. Okay. So, you can see that lot of wiggles getting developed here on the top. Okay. If I can switch off this legend, you can probably observe it better. Okay. Okay. So, you can see that near the discontinuity there are a lot of wiggles. Okay. And now what I will do, I will do the McCormack, but McCormack is very tricky for this problem. Okay, let us see if it works. Yeah, it has worked, but you can see there is a large jump here. Okay, this side it is different, this side it is matching, but there is a large jump in near this point, near the expansion region. Okay, using the McCormack scheme. Okay, now let us plot all of this together. Okay, this was a movie, so let me just show you the. Okay, yeah. So, in this I am comparing all these schemes. Okay, as you can see here that I use this Lex-Frederick and store it as R, L, U, L and P, L, L for Lex-Frederick. Then I use McCormack, store it as R, M, U, M, P, M, okay, the M for McCormack, and then I use Richtmeier and I store is R, R, U, R and P, R. Okay, and then I am basically comparing all those results. So, okay, so let me run it again. Okay, yeah. So, let us look at the density first. Yeah, so you can see here. So, I have plotted that analytical results also. So, if you zoom that in, let us say at any region here, Okay, you can see the black line which is the analytical one. Okay, the lax fabric which is basically smearing out, but does not have any oscillation. It has got the dissipative error in the leading term. Okay, Richtmeier and McCormack, okay, both have got basically dispersive error, and that is how the solution looks like. Okay, where you have discontinuity. Okay. So, the McCormack has got some issues when it tries to go near the expansion fan. Okay. Here for example, all of them behave as expected. Okay. Here if you see in the region where the expansion fan starts, okay, not able to make it big. Okay. Here you can see the black one is analytical, and the lax fatigue has the maximum dissipation. Okay, and the McCormack has got least dissipation, but it has got some funny behavior elsewhere. Okay, and then this is Richtmeier. Okay, uh, same thing you can see near this sock also. So, this is my sock. Okay. So, if you zoom that in, you can see that your McCormack is doing good here, and your lax is also better. Okay, and in the Richtmeier or this Laxman-Ruff, okay, you are having lot of oscillations, and the same thing is basically seen in other cases also. Okay, now you have the density, you can look at in the pressure also. Okay, and then you can have this in the velocity also. Since in all of them McCormack has got some funny behavior, as you can see through this line. Okay. So, what we learnt from today's class is that we can use our understanding to code any complex problem also. So, right now we have solved the entire Euler equation for the 1D flow. You can expand it to 2D flow, to 3D flow. Only thing that will change is your index will increase. Okay. And then we have used these schemes like Lax, McCormack and Richtmeier. Okay, but when you are doing CFD, you will use schemes like row scheme. Okay, which is a the derivation of row scheme requires a little bit of time, and I would request you to basically go back and see how the row scheme is derived, and you can probably code it and see how the row scheme is behaving. Okay. So, now I hope you have a basic understanding of how coding is done, how you can write a very simple code. You can convert it to the viscous part also. So, now you have only used the Euler flux. You can also calculate the viscous flux based on the your velocity gradient and the temperature gradient. Okay, and put that together, and then do it, solve it, iterate it, and you can compare the results between different schemes. Okay, and finally, this is only written in MATLAB, but you can use your own basically favorite language, maybe C, C++, Fortran or Python, anything that you want, Julia. Okay, and basically start writing your code. Okay, so we have not discussed much about the boundary condition here, because for example, if you see here, I am stopping it before the sock crosses on the right hand side, right hand boundary, which is at 0.5. Okay, if you do not if you let it go, then you have to basically make sure what kind of boundary condition is using. You might have a wall at the end, okay, where the velocity goes to 0, or you might have a periodic boundary condition, so the sock will keep on going like this. Okay, so that you need to be very careful. So, we will discuss about the boundary conditions in detail. Okay, but as far as the schemes and writing a simple CFD codes are done, I hope you have got a good understanding, and I expect that you go back and start coding simple problems, and we will meet you in the next class. Thank you very much.